Hello, class. In today's lecture, we'll spend time with three diverse subjects: probability distributions, failure mode and effects analysis, FMEA, and physical measurement. There's quite a lot to digest today, so I recommend that you take your time, take some good notes so that you can internalize all the information that we're going to be talking about so that you can apply it in the future. We reviewed the normal distribution, a continuous distribution, earlier in the course. The probability distributions that we'll review today, binomial, Poisson, and Chisquare, are discrete, so they're not continuous. We'll review their formulas and see how their distributions compare to the normal curve. FMEA, failure mode and effects analysis, is one of the most popular and effective Six Sigma tools. It uses a novel concept called the risk priority number, RPN, not to be confused with RPM, so it's RPN, to prioritize activities. I'll help you learn about RPN and also provide a form to help you use FMEA. We'll wrap up the lecture by looking at a few members of the physical measurement family: metrology, tensile strength, micrometers, and optical comparatives. Make sure you have your calculators handy or your computers. Everyone ready? Let's go. Before we take a crack at understanding probability distributions, we should spend time making sure that we all have the same perspective on what probability is. Common synonyms for probability are chance, likelihood, or tendency. In a typical day, we modify the word probability and use it as probably. My niece may tell her mother, "I'll probably get married next June." Our most frequent exposure to the use of probability is when we hear our local weathercaster say, "There's a 75% probability of snowfall by this evening." Although the weathercaster assigns a numerical value to the probability, we question its reliability. From a scientific point of view, probability is the study of random events. Probability and statistics have an interesting relationship. Statisticians use probability to make hunches or inferences about a sample or to describe a population. If you've ever taken a course in probability, you may recall that your instructor used familiar objects such as coins, dice, or cards to help you learn the basics. If you toss a coin, you have a 50% chance of a head and the same probability of a tail. A roll of a six-sided die gives you a 16.67% chance of getting the numbers 1 to 6. If you pick a card from a deck, your chance of drawing a heart is 25%, which is 13 divided by 52. Let's see how we can use statistical inference with probability. Suppose that we toss a die 10 times and we record the number of dots after each roll. After the 10th roll, we learn that every single roll is the number 1. Something seems fishy. One of our theories before we began was that the die is balanced. We reject this theory, our inference, because rolling a 1 10 consecutive times is highly unlikely. This example illustrates how important it is to verify assumptions about populations before making inferences. How many cases do you know of where someone didn't do this and made a false inference? Developing a formula to determine probability is easy. The probability of an event A equals the number of chances N divided by the number of equally likely ways, capital N. So the formula is the probability of A equals the lowercase n divided by capital N. For a coin toss, it's P of A equals 1 divided by 2, or 0.5. We can use a coin, die, and a deck of cards to create simple probability distributions. This will help us prepare for the more involved distributions that we will tackle later. One thing to recognize is that the total of all individual probabilities must equal 1. Before we move on to our probability distributions, let's look at a few key points about probability. The term sample space describes all possible outcomes. It is the set of all sample points. If we toss 2 coins, sample space is 4 because we have the following possible outcomes. We have head-head, 2 heads. We have TT, 2 tails. HT, a head and a tail, or TH, a tail and a head. We toss 2 coins, we use compound probability. This type of probability involves either a union or an intersection of events. A union takes place where either an event A or B occur, or both A and B take place. An intersection occurs where both A and B exist. A union B indicates a union, and A with an upside down U, B, an intersection. Okay, I think we've covered the basics well enough. We need to move on to the specific probability distributions. The first 2 are discrete. This means that integers or whole numbers are used. The binomial probability distribution is popularly applied to attribute data, where you have an either-or type of outcome, conforming or non-conforming, or something that occurs or does not occur. For example, use it to determine if a computer powers up or not, then determine the number of defective computers. If we were dedicating our entire course to probability, we could spend time deriving the formula for this distribution. But since it's not a course on probability, I'll give you the information that is used in the majority of quality or Six Sigma applications. First, we have P parentheses small d. That is the probability of non-conforming units. Then we have the small n. That's the number of samples that or number in the sample that we're looking at. We have small d is the number non-conforming in the sample. Then we have P sub O. This is the proportion of non-conforming in the population. And then we have Q sub O. This is the population of conforming in the population. Once we have this information, we can set up our formula, which you can see. The probability of D, non-conforming units, equals to n factorial divided by d factorial times n minus d factorial times p sub 0 to the d power times q sub 0 to the n minus d power. So again, the exclamation point stands for factorial. For example, 4 factorial equals 4 times 3 times 2 times 1. The good news about this formula and the ones that follow is that a computer program or a special calculator can do the calculations and make the charts for you once you identify the number in the sample, the number of non-conforming, and the proportion non-conforming and the population conforming. Let's move on to the next probability distribution. The Poisson probability distribution, named after Simeon Poisson in 1837, Helps describes situations that involve events per unit of time or per unit of amount. Examples are the number of equipment adjustments in a day or the number of defects per lot of product. If we work on another problem together, it will clarify how to use the Poisson distribution. So first we have some variables. Small letter c equals the count of an event in a given classification. The NP sub 0 equals the average count in the sample. And then we have the letter E, which equals to 2.718281. Once we have this information, we can set up the formula so the probability of C, the count of an event in a given classification, equals to the NP sub 0 to the C power divided by the factorial times E to the negative NP sub 0 power. Now I know that this is a lot to take in and it's also pretty confusing, but let's walk through an example and remember that you typically have computer software or a calculator to help you once you identify the variables. Let's assume that the average count of rejects during 1 minute of an operation is 2. My neighbor Jack wants us to develop a Poisson probability distribution so he can present it to his boss tomorrow. So we want to help Jack because after all, we need to be neighborly. So first of all, we look at P of 0, which is the probability of having 0 count. And that's equal to 2 to the 0 power divided by the factorial times 2.718281 to the negative 2 power. That's equal to 0.135, which you can see there in the chart on this slide. It's the purple slide that corresponds to 0 on the far left of the graph. We continue with that calculation, and then we find out that we have the probability of 1 is 0.271, of 2 is 0.271, and so forth and so on. So what happens is if we add up all these cumulative probabilities to 7, we come up with 99.8%. Remember, our goal is that we want to have all the probability that could exist equal to 1 or 100%. So we can then tell the boss of the different probabilities having the number of defects per minute. So we could take a look at 1 and 2. That represents about 54.2%. That's what we could tell our boss to expect during the run in the minute. We would have probably 54% of defects in that minute of our production run. The next probability distribution I want to share is the chi-square probability distribution. This distribution is non-parametric, which is a fancy word that means we don't know about parameters such as the means or proportions. The chi-square statistic helps us understand these situations. The formula is at the top of your slide. It's equal to sigma times 0 sub I minus E to the I squared divided by E to the sub I. Now again, I know this sounds very difficult, but just keep in mind that 0 is the observed frequency and E is the expected frequency and I is a counter. So let's go back to our friend, the dice, to generate some data. Suppose that we roll a single die 120 times and we get these results. 1, 16. Rolling a 2, 19. Rolling a 3 is 27. Rolling a 4 is 17. Rolling a 5 is 23. And rolling a 6 is 18. Now, our expected frequency is 20. And the way we got that is we rolled the dice 120 times, and we have 6 different possible outcomes of having a 1, 2, 3, 4, 5, or 6 on the die. So we could put together a table to find the chi-square value using those formulas, and we find out that the chi-square value is 4.4. This reflects the amount of agreement between the observed and expected frequency. If we rolled all one number for all 120 tries, chi-square would be 100. And if we rolled 21s, 22s, and so on, chi-square would be with 0. And that's a perfect agreement between the observed and expected frequency. The shape of a chi-square probability distribution is not symmetric because its range is bounded to the left by 0 and theoretically infinity to the right. Its shape is skewed to the right, and the skewness of the shape is dependent on the tail. So you can see that this has a long tail to the right, so it's called skewed to the right. Let's briefly look at 2 other distributions. The first one is called the student's T distribution. This is another non-parametric distribution. It is similar to the normal distribution in that it is symmetrical and centered around 0, but it has more variability. For small sample sizes, it is much flatter than the normal distribution. For this distribution, you substitute T for Z, which is the number of standard deviations for an observation above or below the mean. Then we have the F distribution. This distribution is similar to chi-square and the student's T, but it has 2 types of degrees of freedom, one associated with the numerator and one with the denominator. Degrees of freedom is the statistical term for the denominator of a sample variance of n minus 1. I see it's time for our next topic, so we better move on. You can put away your calculators for the remainder of the lesson. Failure mode and effects analysis, FMEA, can also be used in the improve phase of DMAIC. It is an excellent process measurement and improvement technique. It includes a structure, a process, and a report. The automotive, aerospace, and defense industries have successfully used FMEA for years. As with many new things, you may ask, what does this technique offer that other ones don't? I can't answer this question directly, but I can give you the benefits of FMEA. The first benefit is that it improves customer satisfaction and increases probability or profitability. This should get management's attention. It enables you to take the right actions at the right time. During the design phase of a new product, there is a large amount of uncertainty. FMEA facilitates frequent reviews and updates because it becomes a dynamic document that all team members value and use. FMEA focuses on key inputs before you get too far along in the process. It enables you to analyze the essential elements of what you are currently doing and what you're planning to do. This helps you design quality into your processes and reduce downstream manufacturing problems. FMEA formalizes your process improvement efforts. Rather than rely on a single individual to figure things out, FMEA uses a formal approach to recognize and classify problems in a logical way. It reduces or eliminates confusion regarding how input variables relate to the quality of your outputs. Perhaps the greatest benefit of FMEA is that it identifies risk and quantifies it by assigning a rating for severity, probability of occurrence, and your ability to detect problems. Many of these risks are associated with safety in manufacturing and in use. Increasing the safety for your customers and for your work environment is something that everyone wants. Now that you know about the benefits, let's move on to implementation. Here are the steps that lead to successful FMEA implementation. First, list potential failure activities. This is an exercise that many teams enjoy. They get a chance to talk about all the things that can go wrong. I recommend you use a formal brainstorming session and make sure everyone follows the rules. To get started, create a matrix with all the functions and attributes of a process, product, or service. List the potential failure activities next to each function or attribute. If your product is a bicycle, an attribute is an adjustable seat. A potential failure you could use regarding the adjustable seat is seat loses adjustment while rider goes downhill at 40 miles an hour. The second one is to identify impact of the failure. After you complete your list of all the potential failures, determine the consequences of each one. For example, if the seat loses its adjustment, a rider may fall and become injured. The next one is to rate and rank each failure activity. Use a scale of 1 to 10 to rate and rank the severity, 10 being the most severe. Let's say the severity code for the bike seat is 8. Then determine the probability of occurrence. Assign a probability of occurrence ranging from almost impossible to almost certain. For the bike seat, you could give it a probability of low and rate it at a 6. Again, use a scale of 1 to 10. Then assess the probability of detection. Use the same criteria as you did for determined probability of occurrence. The score is 9. Then we determine the risk priority number, RPN, for each function or attribute. You calculate the RPN by multiplying the rating for severity, probability of occurrence, and probability of detection. If we want to find the RPN for the bike seat, it's equal to 8 times 6 times 9, the 3 ratings we assigned, for a total of 432. Finally, you sequence the functions of attributes by RPN. So you're going to rate the ones with the highest number first to help you prioritize your efforts. And then you're going to define recommended action, assign responsibility, and then put action into motion. And then you follow up and calculate a new RPN. You'll determine new codes for severity, probability of occurrence, and probability of detection after you implement the improvements. In conclusion, be aware that there are 2 types of FMEA, one for design and one for process. Research and development typically uses the first, and operations the second. Let's shift gears now and discuss how equipment can help achieve the measurement element of DMAIC. Before you get the wrong idea and believe everything that has to do with the measurement element of DMAIC deals with statistics or diagrams, I want to talk to you about the physical aspect of measurement. If you review the Six Sigma body of knowledge from the American Society for Quality, they include a few sections on physical measurements. We don't have time to review all the measurement methods and instruments, but I will give you information on the basics. You may not know it, but there is a science of weights and measures. It's called metrology. In addition to addressing weights and measures, metrology is also concerned with the study of measuring devices. The purpose of metrology is to verify the accuracy of instrumentation used in engineering, physical science, information technology, and biological applications. Metrology also makes sure that international standards such as ISO and world-class precision is achieved. Let's take a look at a concept and two types of instruments that help assure high levels of quality. So we have tensile strength. Tensile strength is the load at which a material, usually tested under laboratory conditions, can be expected to break. It's measured internationally as Newton per square meter, or in the US, pounds per square inch, PSI. For example, if you want to test the tensile strength for rope, you wrap each end of the rope around two large diameter capstans and slowly increase the tension until the line breaks. Tensile strength can also be measured for liquids as well as solids. A tree draws water from its roots to its upper leaves by using capillary action. Air pressure also acts to break the pull of water. The breaking force of a rope is known as newtons. If you apply too much force to a material, it will break or lose its elasticity. It won't go back to its initial shape. The ultimate tensile strength, UTS, is the force per unit area at which it breaks into. So next time you're using a rope at your company picnic tug-of-war match, ask the picnic coordinator how many newtons the rope has. This will give you a golden opportunity to talk about tensile strength. Let's take a look at two devices, one relatively simple and one complex. A micrometer is one of the most accurate mechanical devices. Its error is only 0.005 millimeter. This instrument has been around since the 17th century. You use a micrometer to measure very small thicknesses and diameters of wires and spheres. Suppose you want to measure the width of a pencil. You rotate the body of the micrometer, called a thimble, to open and close the measuring rods, also known as jaws or an anvil and spindle. Once you secure each rod on both sides of the pencil by using the ratchet knob, also known as a friction screw, you have an accurate measurement. The thimble rotates around a cylinder which has markings every 1/2 millimeter. The left side of the thimble has markings all around it. The line labeled 0 is the primary pointer. When it lines up with the central horizontal line of the cylinder, the distance between the measuring rod is set perfectly. Optical comparators have been around almost as long as micrometers. They are versatile and cost-effective instruments that help quality personnel see and measure a variety of features. They come in all shapes and sizes, which makes it challenging to know which one suits your application. Optical comparators contain the following options. First, screen size and lens magnification. Users often ask how large the viewing screen should be. The answer depends on the types of measurements you plan to make. Evaluate the screen diameter ranging from 12 inches to 30 inches and the magnification, usually from 10 times to 100 times, to set your field of view. A 12-inch screen diameter at 10 times magnification gives a 1-inch field of view. By contrast, a 30-inch screen at 100 times magnification can give a 0.3-inch field of view. Easy on the eyes. Next, we have benchtop or floor top for the optical comparator. This choice depends on the size and weight of the parts you measure, floor space, required screen size, and cost. Benchtop models are lighter, smaller, and have lower load carrying capacities and measuring range. They are suitable to measure small, lightweight parts. Floor models are heavy duty and good for measuring heavy metal parts. Then we have optics. Optics are the heart and soul of a comparator because it's the image that's measured, not the part itself. Optics must be free of distortion, produce a flat field where the image is in sharp focus, and have excellent resolution. Optics technology ranges from a projection lens, magnifying an object and directing it by using a single mirror, to elaborate relay lens systems that allow coaxial illumination. Other considerations for optical comparators include vertical or horizontal projection, type of readout, automatic edge detection system, and measurement software. This concludes our lecture for today. Probably this has been the most challenging lecture of the semester. So I highly recommend that you go back and watch these slides a second time. Make sure that you take really good notes, and make sure that you are able to map the study guide I provide later on to these slides to help you prepare for the quiz.